Most people complain about related rates because they're not accustomed to these types of problems, these word problems where you're thinking about how to apply these ideas. And I understand why, because I used to go to a school myself, and they just don't train you for intelligent kind of things. They kind of, especially in most of these math classes, you'll end up learning things that are just not important. The only two things that are important out of a first semester calculus class are what is a derivative, and two, where do I use this information. So 99% of the people are never going to use any of those tools to calculate derivatives in their entire life. The only time they're going to be using them is in school when they're not learning anything practical. The only people I could see that might use them are a theoretical mathematician, obviously. That's what your job is really, is to figure out how to develop new mathematical tools. And it's good to know how the other ones work in relation so you can come up with a new one. And the other people I see that could possibly use it are computer programmers, so they can explain to a computer how to do this sort of thing so we don't have to do it anymore. But most likely the code for these things already exists, so it's a complete waste of time anyways. But even engineers, most of them are never going to calculate something in this kind of way, where they're going to be like, well, I've got an equation for this, let me take the derivative. They're not going to be doing that, and even if they did have to do that, they're going to use a computer for it. They have computer algebra systems that can do it very quickly. There are even free places on the internet like Wolfram Alpha. You can put an equation in there and it will give you the derivative. So it's a waste of time. And even if you were a theoretical mathematician or someone else that had to use this, again, this is the only important part of calculus. So the reason calculus is important because it's an excellent tool. If we did not have reasons or questions that needed to be answered using calculus, then it would be no point in learning them. So, and especially if you're a theoretical mathematician, then you're coming up with tools. If you don't know what people are trying to solve, or what people are looking for, then there's no way you can come up with anything useful unless you invent something useless. So, I just wanted to emphasize how important these are, and I really wanted to emphasize it because I know that in schools they spend all of their time emphasizing the things that are stupid. But let me come up with, I guess, an example. Well, here, why don't you go ask, if you're in a school like this, go ask any teacher, any engineer, or anyone how to prove pi or prove Pythagorean theorem. I guarantee you 99% of them will not be able to do it. Why? Because it's not important, and it's the same thing with these derivatives. It's not important to be able to calculate them because it's easy. It's important to understand what they are, and that's where learning about what a derivative is comes in. But after that, all that's really important is how to apply it. It's the same thing with Pythagorean theorem. I'm almost certain that 99% of the people will not be able to tell you exactly how to prove it. But it's not important. What is important is how to use it. It has many, many applications. And that's why it's important. It's not important to sit around thinking, like, how do I calculate pi? I've got a button on my calculator that can give me pi. So I don't need to spend time learning how to do it. So that's my point. I guess another example would be as if I opened a driving school and all I did was teach people how cars work, which is fine. I'm not saying that being able to calculate derivatives or learning how cars work is bad, but the only people who really need to know how cars work are mechanics. To drive a car, that has nothing to do with, I guess it does have a little to do with how cars work, but you don't need to know how a car works. All you need to know is that the wheels turn and the steering wheel turns in the other direction, there's a brake. And that's it really. And it can run out of gas. Besides that, I don't need to know how anything else works. It's nice if I do, but its purpose is to get me from point A to point B, and I should spend my time, or if I would spend my time learning how to drive, and not at least teaching people how to drive. Otherwise, rather than teaching people how cars work and then releasing them out onto the road and say, all right, well, you can drive now, and them having never been on a road, don't know anything about traffic signals or anything, it would be a disaster. And that's how often I see a lot of people who are in a kind of the more medieval style education systems where they're learning, these textbooks are basically the same from 500 years ago, where people didn't have calculators, didn't have computers, didn't have all these things, where it is absolutely necessary that everyone should be able to know how to calculate these, because there was no computer or no anything that was going to be able to do it for you. So they haven't been updated, but as I said, I don't really have time to go around updating it into arranging this material into a rational manner. I just don't have that kind of time. So I'm still going to go through these problems anyways, but just understand that if you're in a place and they're focusing on how to calculate these things, it's really completely unimportant. It's just a complete waste of time, especially if you're in some field that's not even related to math, engineering, or computer engineering. It's a complete waste of time for you then. If people come up to you and say, I've got this rate, I've got this rate, I've got this rate, this is happening at this pace, what you need to know is figure out how to get those things to mean something, and being able to calculate rates is going to be useless. So let me just get straight to this problem then, after that lengthy prelude. So air is being pumped into a spherical balloon so that its volume increases at 100 centimeters cubed a second. How fast is the radius increasing when the radius is 50 centimeters? So the first thing to do with these types of problems is to figure out what information I have, or any type of problem really, whether it be a math problem or any problem in general, a chess problem, doesn't matter. To figure out what information do I have. I've got 100 centimeters cubed a second, that the volume is increasing, and I'm looking for how fast the radius is increasing. So this is what I'm looking for when the radius is at 50 centimeters. So the first thing I want to do is try to think about what's going on. I've got a balloon, a spherical one. Looks like a mushroom cloud, but that's fine. So I've got a balloon, and let me just think about it just without any math involved. If I've got a balloon and I put one breath into it every time, so think of the volume, one breath, and they generally tend to be about the same every time. So we can say that the inflow is constant. So every time let's say I've got an empty balloon, every time I put in one breath, it's going to get bigger. But by how much? When I put that first breath in there, the size is going to increase 5-fold or something like that. But after I put in, let's say, like 10 breaths, 8 breaths, something like that, the balloon doesn't get as big anymore. It might double in size the first time, something like this. Then after the next breath, it might only get a little bit bigger. So clearly what's happening is that the rate, as the volume increases, is decreasing. The radius is increasing. So if I put one breath into a small balloon, it's going to increase hugely. If I put one breath into like something the size of a hot air balloon, nothing's going to happen. So clearly the rate is not the same. The rate at which the radius is increasing is not going to be the same the whole time. And this is what I'm looking for. But this is just kind of just like a way just to think abstractly about the problems. This just so happens that this is just a very, very simple one, but sometimes it's not always going to be completely obvious what I'm looking for, and sometimes it's just helpful just to draw it out and think about exactly what is happening, what's going on to the system. The volume addition is the same. It's just helpful just to stop and think about exactly what's going on. It just so happens that this system just has basically like no moving parts, so it's just very easy. So maybe I'm being confusing by even thinking about this. So actually, if you didn't really get this part, then just forget about it. So let's just go back to the stupid part where we think about formulas and whatever dumb stuff. Anyways, so we've got the volume and we have radius. So I need to relate these two rates. One formula that I've got that has both the radius and volume in it is the volume of the sphere. The volume of the sphere is equal to 4/3 pi r cubed. But the information I have is the rate, what I've got so far is the volume rate of change with respect to time, 100 centimeters cubed. I'm looking for the rate of change of the radius with respect to time. I don't know what that is. And the radius at 50 centimeters. So with this example over here, what I was trying to explain is that at different radiuses, the rate of change is going to be different. If the radius were 0, then this would be a lot higher. As this number gets bigger, this number is going to get smaller. That's what's evident from just thinking about this balloon. So I've got a formula with both of these in. So now what I'm going to need to do is get a formula that has the rate of volume change and the rate of radius change. So what I can do is take the derivative of both sides that, with respect to time, not to v or r, but with respect to time. If I do that, this is going to become a constant, but then I use the chain rule, and I get dv for dt. And really what it is just think of this as like x and y, but it's just like the way I would normally do an implicit differentiation problem. Sometimes that throws a lot of people off because there are a lot of different variables. All of a sudden I've got v, I've got r, I've got t. Just take it as a normal problem. Don't let the different variables throw you off. I'm taking it with respect to time because time is what I'm dealing with here. I'm dealing with seconds. So as a result, this is going to become a 1, and then I use the chain rule, and it's just like any other implicit differentiation problem, even though it might look a little confusing. So I'm going to leave this here for now, just to kind of show how it's just very, very nothing special is going on here. So now this is a constant, so I'm going to pull this out in front, and now I'm going to take the derivative of r, so I'm going to get times 3 r squared, just like a regular derivative, and then I'm going to use the chain rule as well, so I get dr dt. So that's the other part that normally throws people off. Normally the most problems people have are with just analyzing a set of information, because in most of the time in math classes, that's what they're not teaching you how to do. They're teaching you how to do things that calculators can do. That it's just, you don't really gain anything out of it. That's what makes what humans' jobs are right now is to be like eyes and ears for machines. I can't really. It's just they can't really take in information. Their programming's not so great where they can look out into the world and analyze things. I've got to be able to find that useful information and give it to them to solve. So it doesn't make sense that I'm going to be. I just understand how people have problems with this. So just, especially if you have problems with it, really just focus on what it is we're looking for and trying to set something like this up, as it's really not that hard. But after just being able to analyze what information I'm looking for, and what information I've got, then the next part that really throws people off is just taking it with respect to time and just the different variables. And that's just something that after you've done it a few times, you realize it's not different from any other problem. It just looks confusing at first, but after you've done it a couple of times, it's just like anything else. So I'm going to simplify this. So these will cancel. So we get 4 pi r squared dr dt. So I'm looking for dr dt. So I'm going to divide this out over to the other side. And now all I'm left with is just to replace all of my known information. I know what r is, that's 50 centimeters. I know what dv/dr is, that's 100 centimeters cubed. So I've got everything I need to solve this problem, so all I do is just put this stuff in there now. And another thing that's important is to put the units in there, because often you'll be able to tell if you did something wrong if the units don't make any sense. So I definitely recommend. Some people don't like putting the units in there because I just don't do it. A lot of times I don't do it because I've done so much work in chemistry that it's just second nature to me. But especially, it's just a good way of double checking and see what's going on. Oh, not equal, times 100. See, I would have made a mistake right there. So if you put this into a calculator, let's see what you get. Get 0.0 0.127 approximately. So this is the answer. Oh. So I made a mistake with the units as well. So there's a second. Okay. Now that's correct. See, sometimes you just gotta make sure. Some people would actually mark this as incorrect. I remember that was really annoying in my chemistry class. The unit's wrong, but anyways. So what does this answer mean? This means that when the radius of the balloon is 50 centimeters, that at that instant in time, the radius is increasing at 0.0127 centimeters a second. So that wasn't that bad. But it's good to practice these a lot, because these are going to be being able to solve these kinds of problems are what are going to make someone a good engineer, or one that just has a degree on the wall that doesn't really know anything, really.